Assalamualaikum. Good afternoon.
Waalaikumsalam, sir.
Salam, sir.
Right. Can you see my slide?
Yes, sir.
Yes, sir. Yes, sir.
Okay, guys. This was the solution that you have done. I think there was one session that I have mistakenly find the value for sigma A. The sigma A should be, for this plot, the sigma A should be minus 4.33. So this sigma A should be equal to minus 4.33. And this was the mistake. So please take note on this. Right? Okay, guys. Is that clear? I think that was the session that was on Thursday 8 to 10, last Thursday. So the sigma A should be minus 4.33. Right, guys. If you look at the procedure that you have here for the lag compensator, so first thing first, of course, you need to have your plot, the root locus plot of the original system before you can come out with the dominant pole. So as you look at what that you have here, the dominant pole will be the point of where the intersection of zeta equal 0.174 line with the locus that you have plotted. So I did remind you that you won't be able to obtain the dominant poles more than a single mean number after the decimal point, because we are just going to have a sketch. Probably the most precise that we can have, it will be on your graph paper. So what that will be the expectation, it will be just one value after the decimal point. So as what that you have here, it was the solution that come from the tools like MATLAB, and definitely it will be the exact point that you probably going to have up to a 3 mean number after the decimal point. So this point of dominant pole, this is the dominant pole, the point of which you have the intersection of your locus and zeta equal 0.174 line. This point. So when you have the point of this dominant pole, it will affect your answer. So it will affect the solution that you are going to have for K. Your K probably will not be exactly as K equal 164.6. So having the K that is not the value that is the exact value of what that is in your slide, you are going to have your answer that probably is going to be quite different from what that you have here. But the most important thing is you know that you need to know about your dominant poles, and after that you are going to use that dominant pole value to be substituted in your actual equation from the original equation. Then you can get your K. So K will be 164.6 in this solution. So is there anybody that would like to share the solution that you have had? Any one of you guys? Hello? Okay. So I'm just going to refer to what that we have here. So with K equal as 164.6, then you can find your KP. Your KP now is 8.23. I'm just going to recap what that you need to have for you to come out with the lag compensator. Then knowing that you want to have the improvement of tenfold improvement, therefore you are going to have your error that will be 0.0108. This is considered as the desired error that you want after you add in the lag compensator. Then after that, you will know what that should be for your KP. Having the KP with the value of K, it will be the current KP, and after that you work for the tenfold improvement, you will know the new error that you need to have. Then you will know about your new KP. So the new KP that you should have, it must be 91.59. So from here, you're going to have the equations of the ZC over PC is equal to KP new over KP old. The original KP that we have will be known as KP old. The KP after you want to have the tenfold improvement will be your KP new. So ZC over PC will be KP new 91.59 over this 8.23, the KP that you have after you get the K equal 164.6. This is considered as the KP for the original system. So you will have the ZC over PC will be 11.13, and then just select arbitrarily one value of the PC that is close to the origin, and you can take the PC that will be equal to 0.01. Then you are going to have your ZC that will be 0.11. 0.111. So this is coming from ZC equal to the 11.13 time with the PC that you have selected. Okay. Any question on this? Anything, guys? Hello? You have any question, guys?
Sir.
Right. So then we are going to talk about the next thing that you are going to have for the third and fourth poles. So the third and fourth pole, as according to the explanation here, you are going to have it to be as minus 11.55 for the third poles and minus 0.101 for the fourth pole. So this will be the poles that you are going to consider as the poles after you have your consideration on the dominant poles. So it will be a bit different of what that you are going to have, as you have to have another consideration right after you consider for the ZC and PC, then you can have these third and fourth poles. So I'm just going to skip this for now, because we can actually look at it as we work on the MATLAB later. And I'm going to get back to this third and fourth poles explanation. Right, guys? So the poles that actually represented by this pole, minus 11.55 and minus 0.101 for the fourth pole, you can actually have this after you have the system with the compensator. So we are going to look at it later. So this pole is actually the pole that you have after you redraw everything, redraw the root locus with the lag compensator. You add in the lag compensator that you have had, and then you redraw it. And this is going to be the poles that we are talking about for the third poles. That is minus 11.55. And the fourth poles that will be minus 0.101. We are going to get back to this after we do the simulations in the MATLAB. We'll do the simulation in MATLAB. I think probably it's going to be next week or next 2 weeks. Right, but the most important thing is you must know that there will be the steps that you need to know before you can come out with the compensator equation and have that to be as way for you to solve for the lag compensator. And the rule of thumb, it's always going to be the condition for which that you are going to have your ZC is greater than PC. How do you know that you are going to have the value for this PC and ZC? You're just going to assume one value for the PC that will be close to the origin. As for the solution that you have here, you take the PC is equal to 0.01. Right, guys? Any question? Anything? Guys, do you have any question?
None, sir.
No, sir.
Right. So this is the description that you can actually have as you look at the output response. So the output response that you are going to have will be the output response that shows the improvement of the steady state error, because you are using you are actually dealing with this lag compensator. So for the uncompensated will be with this black color. And once you add in the compensator, the lag compensated response will be in the blue color. So we have the difference that is going to be on the difference of your input and output to be closer when we add in the lag compensator for the steady state part, which means that we are going to have less steady state error by adding the lag compensator. So that is going to be the things that why we want to have the lag compensator. The lag compensator will be the one that we use for the improvement of the steady state. Right, guys? Okay, let's get back a bit on this. Do you have any question that you would like to ask? Anything? On the design procedure? Anything, guys? So I think it's quite straightforward. Do you have anything that you would like to ask? So if let's say you are going to work with the system that will be type 1 system, so you need to deal with the static error constant of velocity. You need to find the KV value. Same goes to if let's say the system is type 2 system. So it means that you need to work on the acceleration static error constant, that is Ka. Right? Okay. Do you have any question? Anything?
Sir, how do we identify whether the system is type 1 or type 0 then?
Type of the system will be determined by what that you have at the denominator. So the common equation that you are going to have for the transfer function will be this. This is the transfer function that you are going to have in general, where it is going to be K times S plus Z1, S plus Z2, and so on, over S to the power of N times S plus P1, S plus P2, and so on. In certain reference, it will be as the final pole that you possibly is going to be S plus Zm. We're just going to take it as the number of the zeros that you are going to have. And S plus Pn, Sn is going to be the total number that we are going to have for the poles. And we are going to actually look at this n. So this n will determine whether the system is going to be type 0, type 1, or type 2. So as what that you have in your example here, this s to the power of n will be s to the power of 0. This is the pole, this is the pole, this is the pole. So that's why we are going to consider for Kp. If let's say at the denominator, once you have the denominator in the terms of factors, because you can have the denominator and numerator in terms of polynomials or factors. You have to convert it. If let's say your denominator in polynomial, convert it to the factors term, and you are going to have your denominator with this s to the power of n outside of the factors for your denominators. So if let's say you are referring to this example, there will be no s outside of the factors that you have here. So it has to be s to the power of zeros. So this s to the power of 0 that you have here, showing that the type of the system will be type 0. And you need to find for your KP. Right? Does that make sense to you?
Yes, sir.
Okay. Anything else? So if, let's say, I'm just going to put it here, the n here determine the type of the system. So if, let's say, the system is type 0, so you need to find KP, because this will be the only value that you are going to have as the static error constant if you consider for type 0 system, the KP, I mean. So type 1, it will be KV, the velocity static error constant. Type 2, it will be KA. Yes.
Okay, sir.
Okay. So I don't really like to have this to be explained with the redundant n value, and they are not the same, but you can actually find some of the book will somehow explain to you as S plus Zm to be the number of zeros that you're possibly going to have up to m number, and S plus Pn will be the possible number of poles that will be n for the poles that you are going to have for a system. But just bear in mind the n that I have shown it here will not be the same as the n for this Pn. Right?
Okay, sir.
Okay. Any other question, guys? Anything that you would like to ask? I'm just going to touch a bit on this one later. But before that, do you have any question? Anything?
Sir, the formula to calculate KP, KV, and K will be the same, right?
No, it won't be the same. It is not the same. Any other question? Okay, I'm just going to get back to your confirmation just now about whether the KP, KV, and KA will be the same or not. KP, KV, and KA will not be the same. Okay, let's just have this as another example for the S to the power of n. As you look at the example that you have here, your S is outside the factors that you have for the denominator, which means that this will be S to the power of 1. So what that you need to find, it will be the KV. Right? You need to find the velocity static error constant. So that's why you are going to work as you find this KV. Okay, let's get back to the statement that was just made by your friend. The KP, KV, and KA will not be the same. Whenever that you want to actually find it, the KP is equal to limiting as approaching 0 GS. So this is the KP. As you want to find the KV, KV will be limiting S tends to be zero as s approaching zero as gs, and ka will be limiting as s approaching zero s squared gs. So this is the formula or the calculation that you are going to have for you to find the static error constant. They are not the same. Right, guys? Any other question? Even the static error constant will not be this, even the steady state error will be not the same when you consider for the Kp, Kv, and Ka. The steady state error for the Kp, it will be equal to 1 over 1 plus Kp. The steady state error for the Kv, it will be 1 over Kv. The steady state error for the Ka will be 1 over Ka. If you would like to have further revision, you can refer to the steady state chapter of control system. Right? Do you have any other
Okay, sir.
question? But at least I have already responded to your question, whether this Kp, Kv, and Ka are the same in terms of calculations. They are not the same. We are going to have other formula for every and each of the static error constant. It is actually can be proven. You can see from the lecture notes of the steady state in the subject of control system. Right, guys? Do you have any other question? Nope. Okay, I'm going to allow you for about 8 minutes. Let's get back at 12:45, and we are going to continue to the next chapter. I'm going to have this to be as chapter number 3, and we are going to look into the lead compensator. Right, guys? If you do have a question, by all means, you can still ask me before we begin with our new chapter. Right? Okay. Let's get back to the session in a bit. Okay, right, guys. Any question on the lag compensator? Guys, before we move into this lead compensator, do you have any question?
No, sir.
All right. So let's dive into this. This is the other compensator that is known as lead compensator, and you can have it to be as the general equation for the lead compensator will be KCS plus 1 over T over S plus 1 over alpha T. So as we are going to take the alpha that will be in between 0 to 1, it will be more than 0 and less than 1. So we will know that these conditions of alpha will come out with the rule of thumb of which that we are going to have the ZC will be greater than, sorry, the PC will be greater than ZC. So this is the rule of thumb of this lead compensator. So it will be oppositely with what that we have in the lag compensator. So what that we are going to have here, as we consider the PC that will be greater than ZC, definitely 0 is going to be to the right of the pole. So what that we are going to have later on, the value of the 0 or the ZC for the compensator will be less to compare to the PC. So in other way of having this to be as your equation for the compensator, you can have it to be as Kc times S plus Zc over S plus Pc. So the Zc is 1 over T and the Pc is 1 over this Zc is 1 over T. The Pc will be 1 over alpha T. Right? So I normally going to just refer to this. I mean the S plus ZC over S plus PC. So this is roughly the idea how that you can have it to be in a way that using the lead compensator, you can have the system to have the improvement on the transient response. So when we talk about the transient response, we are talking about the oscillatory part of the response. So if let's say you are going to have the equation that will be gs is equal to 1 over s plus 1, so it means that you are going to have your pole at 0 and poles at -1. So if the gc that you are going to have it to be as one constant value, you possibly going to have the locus with a straight vertical line, and this straight vertical line will show that you have your consideration from k equal 0 up to k equal infinity. When you consider the plot with the starting point and ending point, for the poles, you're normally going to have it to be as k equal 0. So this is k equal 0. As you need to have the representation of root locus that will be in between 0 to infinity, this vertical line will show to you where that you are going to have for the k equal infinity. Right. So next, when you include the GC, that will be equal to k s plus 2 over s plus 10. This s plus 2, s plus 10 is the equation that you are going to have with the compensator that is already added in the original system. You are going to have the plot that will be look like this. So it will be the plot of the root locus to have a movement to the left of the S-plane. So having it to be as it will move towards the left of the half plane, the S-plane, it shows that you are going to have it to be as an improvement of the transient response. So this is just an example for which that you are going to have the ZC equal to 2 and PC equal to 10. So it meets with what that you're supposed to have for the rule of thumb of the lead compensator. The PC should be greater than ZC. Okay. Anything, guys? Yeah, one way to understand about this S-plane, as we are going to have what that will be the plot for the root locus, and it will be far away from the vertical line or the imaginary axis. So it means that there will be an improvement that will be on the original system. So as the plot moving towards the left of the S-plane, more to the left, so it means that there will be an improvement. So the improvement that we are talking about possibly is going to be the improvement for the transient and as well as steady state. Because the more left that you are going to have on the plot means that you are going to have better performance of the system. Right. So as we are going to have it to be with the other value of compensator instead of s plus 2 over s plus 10 before, we have it to be as s plus 2 over s plus 20. So it will be the conditions that we are going to have the system that will be with further improvement. So we can have it to be as the system known with the fast response system and well-damped system. Fast response means that we are going to have the system to be in a way that it will take a shorter time to compare to what that it was before and reach up to the steady state point for the system. So that will be what that we are going to have for the improvement of having the value of PC that is going to be a bit farther in terms of the left of the S-plane. So here we got the PC that will be 10, and here we got the PC that will be at 20. Of course, both of them will be at -10 and -20 of our plot. So if let's say you're just going to have it to be as -10, you're probably just going to have it to be with the curve that has to be in this plot. And if let's say you are going to have it with the poles that will be minus 20, you possibly is going to have it to be like a circle that you are going to have for the root locus plot. Okay. This is just the example to show to you how that you can have the lead compensator to have the system to be improved in terms of the transient response performance. So this will be what that you need to have to come out with the lead compensator design. So this is one of the way, but I'm not going to use this. You can also refer to this if you want to. I'm going to use this design procedure. Okay, this will be the design procedure that I'm going to show it to you. So first thing first, once you have the system, you need to find the sum of angles at the desired location of one of the dominant closed loop poles with the open loop poles and zeros of the original system. So that will be your first step. I think I'm going to just go through the procedures that we will have for the lead compensator design along with the example that we are going to refer to. So let's refer to one example that we are going to have it to be here. So this is just one example that you are going to have as you want to consider this gripper tool controller. So the open loop transfer function with negative unity feedback of a position control system for a gripper tool is given by this 1 over s plus 2 squared s plus 3. So first thing first, you need to sketch the root locus as it must be with the condition of k in between 0 up to infinity. Then we are going to determine the dominant closed loop poles. So the undamped natural frequency for the dominant closed loop pole, we are going to take it as omega n. And for the value of k that we are going to have it to be considered, it will be at the zeta equal 0.5. So we have to have the plot, and then from the plot, we will have the point for the dominant closed loop poles. So these dominant poles will be the one that after we have the plot. So this is going to be the next question, next part of the question, where that you need to design a lead compensator to reduce the settling time, the TS, by a factor of 2. And you are going to still maintain the consideration at the same dominant poles where zeta equal 0.5. And then at last, for the sub-question of D, we are going to find the steady state error. So if let's say we are having this to be as the improvement of the lead compensator, what that will actually affect with the adding of lead compensator, it is actually going to affect the transient response, but we can still find the new steady state error at this additional lead compensator to be in the system. So you need to find the steady state error of the lead compensated system to step input, and you have to explain briefly how to improve the steady state error. So if let's say we are going to just have this to be as what that we already understood from the lag compensator, definitely if let's say we want to improve the steady state error, we need to add the lag compensator to the system. But we are still can have the steady state error determined when we add in the lead compensator. So this is the solution that you're possibly going to have. So first thing first, in the sketch of the root locus, you need to find the poles and zero value. You have two poles that will be existed on the same point, that is -2. So you have poles that is -2, -2, and -3. And as for zeros, you do not have zero in the system. So this will be the zero and poles that you are going to have for the system. Do you have any question for zero and poles determination in the example here? Any question? So this is s plus 2 squared. That's why you are going to have two repeated poles that will be at this -2. And the other pole will be at -3. No zero. Any question? Okay. So as for the behavior at infinity, you are going to have it to be as -2.33. So -2 plus -2 plus -3 minus 0 over 3 minus 0. So it will be -7 over 3, and we are going to have it to be as -2.33. Any question? Guys? Do you have any question? Okay. The theta k will be 60 degree at k equals 0, k equal 1, it will be 180 degree, k equal 2 will be 300 degree. Do you have any question, guys? By all means, anything? Anything, if you would like me to show it to you? Anything else? Hello? Guys, do you have any question? Hello? Okay. J omega axis crossing, you can use the Roux-Swiss method, or letting S equal to J omega, it will be at plus minus J4. Breakaway point will be at the point for which that we are going to have these two repeated poles, and it will be at this -2. So this will be something that you can actually have this to be as an explanation, since the poles exist at the same point of -2, your breakaway point will be at this -2 point as well, without considering it with the differentiation method. You can do it that way. If you do the calculation with the differentiation method, you will actually have the answer for the breakaway point will be at -2 anyway. Right, so this is going to be the plot. So once you have the plot, you can actually have the dominant poles. So anything that you would like to ask for the plot. I'm going to use the same plot to for me to actually consider for the lead compensator. But the plot that you're supposed to have will be the plot with this locus. There will be 2 points that 2 poles that we are going to have exist on this -2 point, and this -3 will be just another point for the poles. Okay, guys, anything? Okay, so try to have the plot. Then from the plot, zeta will be 0.5. Therefore, you will know about what that you are going to have for the dominant pole. So the dominant pole that you are going to have, as I'm referring to this plot, I'm going to have it to be at this minus 1.1 plus J 1.9. So this will be the point minus 1.1 plus J 1.9. So this is going to be the point. So I need to find the theta where the zeta is equal cosine theta. Since zeta is 0.5, so I'm going to have the theta as theta equal arc cosine of 0.5. Got it, guys? And the theta will be 60 degree. And I'm going to plot this line from the intersection of the line that refer as zeta equals 0.5. I'm going to find the dominant poles. And the dominant poles that I'm going to have is this. Minus 1.1 plus J 1.9. This point. Can you see my cursor, guys?
Yes, sir.
Yes. Okay. Then once I have this minus 1.1 plus J 1.5, I can actually substitute it in the original equation and find the K value. The K value, if we refer to the plot that I have here, it will be 11.876. I can get the K value up to this 3 mean number after the decimal because I'm going to have it via calculation. Right? Any question? Guys, do you have any question? Okay. Let's move. So now I actually responded to the question that I have for this A and B. Now let's move to C. The settling time that I'm going to have here will be 3.64 seconds. I need to consider this settling time. So how do I get this? Guys? TS equal 3.64 seconds. How do I get this? And I want the improvement of the settling time to be by a factor of 2. How do I get this 3.64 seconds? Hello, guys. Guys, how do I get this 3.64 second? Hello? Guys, look at the question here. You need to have this as you want to consider for the lead compensator to reduce the settling time TS by a factor of 2, and you want to maintain the zeta that will be at 0.5. So zeta equals 0.5 means that you are still referring to the same dominant pole. So the dominant pole that you have here, it will be SD equal minus 1.1 plus J 1.9. So this minus 1.1 that you have here is actually the value of, guys, the value of your sigma D. And sigma D is equal to zeta omega n. So what that will be your zeta omega n? In this consideration, it will be 1.1. So the TS is determined since it does not mention whether it's going to be 2% criteria or 5% criteria. The default for the settling time will be 2% criteria, where it comes from 4 over zeta omega n, or 4 over sigma d. Your sigma d is 1 minus 1.1, so it will be equal to 4 over 1.1. And you are going to have it to be as 3.636 something. So that's why it will be at 3.64 second. This is the common consideration for the settling time, and you have learned this, and it's supposed to be something that you already knew about this settling time, where it comes from this 4 over zeta omega n. Right, guys? So as you want to have the improvement by a factor of 2 and maintaining the damping ratio of 0.5, so TS improve that you want to have, it will be 3.64 second over 2. So you must have the improvement of the settling time that you are going to have later. It will be 1.82 second. Okay, what does this mean? If let's say you want this to be with the improvement of this 1.82 second, so it means that you need to multiply the SD that you have for the original system by 2. So your SD new will be 2 times SD old. This SD old will be this minus 1.1 plus J 1.9. So you are going to have it to be at minus 2.2 plus J 3.8. Right, guys? So this is how that you are going to have an improvement of the settling time to be 1.82 second. Right. Till this point, do you have any question? Because we are going to move to the next one for the design of the lead compensator. And we are going to use this bisectional method.
Sir, I have a question.
Mhm.
How do we know the improvement by a factor of 2?
We are going to divide it by 2. 2 time improvement. So what that we have with this original settling time from the original system, the settling time that we have will be 3.64. So divide the original system settling time by 2, we will have the improvement by a factor of 2.
Okay, sir.
Any other question? So first thing first, you need to know what that you are going to have for the settling time. Does this make sense to you? I mean, the explanation of this? Do you have any question? The settling time that is equal to 3.64. Do you have any question? Okay. So if let's say we want to have the improvement of this 1.82 second for the settling time, we need to have this lead compensator to be designed at the new dominant pole that will be minus 2.2 plus J 3.8. So we're just going to consider at 1 point that will be on the positive part of the J omega axis, and whatever that is going to happen to the overall changes of the system, it will be symmetry about the real axis. So it will be just the work that we are going to have up to now, as we are going to working on just 1 point that will be on the positive side. And then later for the overall plot of the additional lead compensator in the system, we're just going to have the plot that will reflect to the condition of which the plot should be symmetry about the real axis. So no need to consider for both point of the positive and negative of J omega axis. Just focus on 1 point, and the other point or the other plot that we are going to have for the other side of negative J omega, it will be the conditions that the plot should symmetry about the real axis. Okay. So this will be the design procedure. So let's get back to the procedure that we have here. So we need to find the dominant closed loop poles. That will be the first step that we should have. And as for the determination of this dominant closed loop poles or dominant poles that we are going to call it, we are referring to the condition of zeta, the damping ratio, and we are going to have the system that operates with the damping ratio of 0.5, and we already have the dominant closed loop poles or dominant poles. Then in the next step, we need to determine the necessary angle where we are going to have it to be called as phi to be added so that the total sum of the angle is equal to 2K plus 1 times 180 degree. This shows that it must be equal to 180 degree, and the lead compensator must contribute this angle of phi. Right, guys? So do you have any question till this point? Right. Let's look at what that we have until this part of knowing our new dominant pole that will be minus 2.2 plus G 3.8 here. And let's just try to digest how that you can actually work until you get this. So I'm going to allow you for about 7 minutes. So ask me if you do have a question from A, B, and C that we have already discussed here. Then we are going to move to how that we can actually have the design for the lead compensator. I think it would be better if, let's say, you can understand what that we have had before we continue. Right, guys? Can we do so? Guys?
Yes, sir.
Okay. Okay, guys. Any question? My point is actually to leave you with your work. Possibly you want to plot, and we can actually compare the answer from what that I have in my plot and your answer. Uh, or you try to figure out how that you can actually get what that you can refer from the lecture notes. Do you have any question, guys? And that was my point before I'm going to continue to the lead compensator. Do you have any question?
Sir, how do you get the value for K again?
How do I get the K value?
Yes, 11.876.
Take what that you have here and substitute to the original equation that you have here, and you are going to have your K equal to 11.876. Same as this, same as what that you can have it here. Before this, you consider for this like compensator as K equal to 1 over GSHS. And 1 over S plus 1, S plus 2, S plus 10 means that you're going to have your K with S plus 1, S plus 2, S plus 10 for this example. And now, if let's say you refer to the example that you have for the lead compensator, it will be K equal to magnitude of S plus 2 squared times S plus 3 with the dominant poles value. So it means that you're going to have your K that will be the magnitude for this S plus 2 squared, S plus 3, where S is equal to minus 1.1 plus J 1.9. Then you will have your K that will be 11.876. Right?
Okay, sir.
Any other question? Try to do it, guys. Did you get K equal 11.876? Anything else? Okay. So let's move. I'm just going to have this to be as how that you can actually determine the phi angle. The phi angle is actually known as a contribution angle or angle of contribution, where you want to consider for your lead compensator by using the method that is known as bisectional method or bisector method. Okay, this is going to be how you determine the phi. I can just write it as phi plus summation of theta z in minus summation of theta, sorry, p theta zi minus summation of theta pi equal 180 degree. And I'm going to have it to be equal to 86 degree. How do I consider this? It comes from phi plus what that I'm supposed to have for the value that will be the summation of zeros angle in my plot. Is there going to be any value? Guys? Is there going to be any value? Hello?
Yes.
Is there going to be any value? Since I'm going to consider this phi that is equal to summation of zeros angle, is there going to be any value of zero angle that I'm going to have? Is there any zero in our plot?
Again, sir.
No. So it will be 0 minus what that's going to be next? The summations of poles angle. So how do I consider for the poles angle? So that's why it is so important for you to have everything as it will be under the exact scale. Because if you, let's say you have the exact scale of the plot, you do not need to actually consider for the angle by using trigonometry. You can just use your protractor to measure the angle that you are going to have for the poles angle and as well as zero angle if you do have the zero angle. But in this case, you do not have the zero angle. You only have the poles angle. So you need to know the poles angle. And once you have the poles angle in the consideration, I'm just going to put here like the question mark because you are going to have at least 3 value of this poles angle, and you are going to have it to be equal 86 degree. So have your plot, and then in my plot here, I'm going to have it to be 86 degree. Okay. Guys, anything? Anything else that you like to ask? So I'm going to consider the poles angle that will be from this pole to my new dominant pole, from this pole to my new dominant pole, and for this pole at -3 as well to this new dominant pole. So I'm going to get the phi that will be 86 degree. Okay, is that clear? So you just,
Can you repeat again?
right. The contribution angle, the phi will be determined by this formula. Phi plus summation of theta zi minus summation of theta pi. This theta zi is the zeros angle. There will be no zero in our system that we have up to now. The original system will be with no zero. And then we are going to have the poles that will be in our system because we need to find what that will be the summation of poles angle. So how many poles angle that we are going to have? We are going to have three poles angles that come from the -2 and -2 and -3. So how do I consider the angles? I'm going to consider the angles that from the point of -2 to the point of this new dominant pole. And it will be the same point and the same angle that I'm going to have. That will be two poles angles, and the third pole angles come from this -3 point. So this -3 point towards this new dominant pole, what that will be the angle. So once I have that, in my consideration, I'm going to have this phi equal 180 degree. So with the equation that I'm going to use, that will be this. Okay.
Okay, sir.
Right. Okay. So once I get the phi, that will be 86 degree. So I'm going to divide it by 2 because this is going to be the consideration method that I'm going to use, known as this bisector or bisectional methods. So once I have it as it will be 43 degree, so I'm going to plot this condition of 43 degree from the point that I'm going to have it to be as the point from the bisectional of this A, P, and 0. I'm going to put it here, it's going to be like O, A, P, and O. I'm going to have the considerations of the bisectional of this AP and 0, as it will be 120 degree. So by the sectional of this APO angle, it will be with 60 degree. So with this 60 degree, then after that, I'm going to consider for what that will be the point for the PC and ZC. How do I consider for the point of ZC and PC? I'm going to take the outcome from the 86 divided by 2, that will be 43 degree, to be the one that will be on both sides of this bisectors point. So for the, I'm going to call this as, for the left side, it will determine the PC value. For the side that I'm going to have it to be as 43 degree of the left from the bisectors of this AP and O, this will be PC. For the right side, with the consideration of same angle 43 degree, I'm going to have for the value of the ZC. So the value for the ZC and PC will be considered on the same plot. Right? Okay. I don't think that you can actually catch up so much on this until you come out with your own plot. So let's reserve this. Try to come out with your own plot for this example. Then in our next session, the sessions that we are going to have it to be as face-to-face session, we are going to get back to this part. I think that will be better for you to understand the whole thing, rather than I'm just going to show as what that I have in my solution. Okay. Okay, guys? Do you have anything that you would like to ask? So I'm going to stop here at this number 1 here. And I'm going to continue with the number 2 and number 3. And of course, if you do have your plot, you can have your number 2, the determination of this ZC and PC. You just need to know how that you can actually do that. So first thing first, let's just recap a bit on this one. Once you have your new dominant pole on your plot, you are going to point out the location for the new dominant pole. So with that new dominant pole, you are going to have the line from that new dominant pole to the origin and a straight horizontal line to the left of that new dominant pole. So this is the way of how that you can actually consider for the ZC and PC by using bisectional method. So we are now dealing with the lead compensator by using this bisectional method. So once you have this APO angle, you are going to have this to be divided by 2 as it will meet with the conditions of what that we name after the method, the bisectional method. We are going to divide it at the middle of the point that you have for this angle A, P, and O as the angle that you are going to have it to be as 120 degree if you plot it correctly. So divide it by 2. So one side will be with a 60 degree and the other will be with 60 degree as well. So you are going to have this B point, B that showing here. Here, the B point. Can you see it, guys? Can you see my cursor? Guys, can you see my cursor?
Yes, sir.
So now, from this B point, you are going to have the line that represent half of what that you have had for the phi value. So the phi value is 86 degree. Divided by 2, it will be 43. So 43 degree to the left of this B point will be the point for your PC. 43 degree to the right of this B point or this B line will be the ZC value. Okay. So first thing first, you need to have your own plot. So prepare your plot, and once we are going to meet again on the lab session that's supposed to be on this Thursday for 2 groups, prepare this plot and we are going to continue our discussion of how that we can actually come out with the lead compensator. Right? I think that will be good for you to understand the whole thing later. Right, guys? Anything before I'm going to stop our session?
Sir, for the
Ah.
quiz next Thursday, the topic will be covered until which chapter?
Just you plot for the root locus.
So lag compensator will not be in the quiz then.
If lag will be there, it will be just the lag compensator that you need to determine for the K. Because both lag and lead will be the same in the determinations of K. Okay?
Okay, sir.
Do you have any other question? Okay, guys. So I'm going to stop here. Let's see again on this Thursday for the two groups, and the other group will be on next Monday. But please prepare your plot, and I'm going to show to you by working with your plot later. Right, guys? Just wait for a while because I'm going to share with you all your QR attendance. Okay, guys, thanks for your time. Thank you. Thanks, guys.
Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Sir, I cannot scan, sir.
Thank you,
Your name, please. Your name, please.
Nurul Darwisha.
Thank you, sir.
Just wait for a while, Nurul Darwisha, because I'm just going to let the others to scan the QR attendance first.
Thank you, sir.
Thank
Thank
you.
you, sir.
Thank you.
Sir,
Aha,
sorry sir, saya tak boleh scan lah sir.
sekejap
It's okay, sir. Already done.
Oh, okay. Alright. Siapa lagi yang tak boleh tadi? Nurul Darwisha dah boleh. Tadi yang ni cakap kat saya tak boleh scan.
Muhammad
Siapa?
Alif Haikal sir.
Muhammad Alif Haikal.
Thank you
Okay. Ada siapa-siapa lagi yang tak boleh scan?
Thank you sir.
Thank you.
Saya boleh silakan untuk Muhammad Iqbal Hakim boleh, sir?
Muhammad M-O or M-U?
MU. Muhammad Iqbal Hakim. Oh, okay, sir. Thank you, sir.
Ni dah boleh. Okay.
Okay, sir.
Anyone else?
Saya tak boleh scan, sir.
Okay. Thanks for your time, guys, again. Thank you. Guys, I'm going to leave the session now. Have you scanned?
Sir,
Yep.
saya nak inform ada seorang student Azam Azhar, dia accident.
Oh, siapa tu?
Lepas tu sekarang ada kat ambulans ke hospital, saya pun tak tahu.
Siapa nama dia?
Azam bin Azhar.
Sekejap, Azam bin Azhar. Sebab ada student control pun yang accident ni.
Oh, tak, dia modern.
Dia pun baru accident.
Oh,
Ke ini yang accident sesama dia orang ni?
tak tahu saya sebab dia bawa accident pukul 12 tadi.
Oh ya ke? Siapa nama dia?
Muhammad Azam bin Azhar.
Okey, tak apa. Nanti cakap kat dia, dia mesti dah ada MC saya rasa tu. Cakap kat
Ah.
dia fill up dia punya BLE ni sahaja. Okey?
Okay, alright.
Alright, okey. Yang lain semua dah scan ke ni? Yang ada dekat dalam ni? You may leave the session, guys. Izzah, you tak boleh scan? Izzah Khairani, awak boleh scan? Sebab awak ada bagi sign hold up macam tu dekat saya tadi. Boleh sign? Okay.
Tak boleh. Tak boleh.
Semua orang dah scan
Tak, tak.
Kalau dah scan, saya akan remove you daripada session.
Sir, nak tanya. Esok petang tak ada kelas kan?
Oh, tak ada. Sayang itu saya akan bagi tahu sebab normally saya akan buat kelas tu sebagai kelas ganti saja.
Oh, okay. So, maksudnya yang hari Isnin punya still hari Isnin?
Macam biasalah, hari Isnin juga. Jadi hari Khamis, grup hari Khamis dululah yang akan buat kuis. Okay.
Faham, sir. Alright.
Alright.
Thank you.
Thank you. Rugendran, awak dah scan?
Sir,
Dah,
saya
ya?
tak dapat scan ke?
Okey, Hafizam Siapa lagi yang tak boleh scan? Bagi tahu kat saya. MU nama you. MU Muhammad Hafizam.
Saya dah, sir. Saya dah, sir.
MU or MO?
Dah.
Hafizam? Dah
Boleh,
saya
sir.
dah. Dah boleh dah?
Boleh dah.
Okey. So awak boleh keluar dulu daripada session. Saya just nak check siapa lagi yang belum. Anwar dah? Hello, Muhammad Anwar. Okey dah. Saya remove dulu awak daripada session. Nur Izzah, awak tak boleh scan ke? Hello? Okey. Siapa lagi? Saya dah tandakan awak punya attendance, Nur Izzah. Saya remove awak daripada session dulu. Sebab saya nak check yang lain. Alright. Irfan? Muhammad Irfan Rashidi. Hello, Irfan, awak boleh scan ke tak? Aiman boleh scan ke tak? Hafizam dah boleh.
Sir, nanti test tu, quiz tu kena boleh kan?
Macam mana?
request tu hari Khamis kena buat laptop lah sir.
Kena bawa laptop. Bawa laptop dulu dan saya akan tengok semua orang ada laptop ke tak. Kalau laptop ada tak boleh buka VLE pun tak guna juga, saya akan ubah soalan. Okay?
Okay.
So just bawa saja laptop dan ensure yang laptop awak sebelum tu, sebab VLE lately ni saya rasa awak pun face up problem kan. Kadang boleh buka, kadang tak boleh buka. Betul? So tengok nanti macam mana. Alright guys, saya akan tutup session ni. Thanks for your time. Assalamualaikum.
Saya berharap